Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Daniel Angerhausen with us today. Hello, Daniel.
Hi, everyone. Hi there.
Let's see. Let's start off. Daniel, what's your geolocation?
I am in Bern, Switzerland,
Ooh.
feeling the burn. Yep.
So is summer there in Switzerland?
Um, According to the calendar, yes, but not yet really. So it's raining at the moment, but it's getting better, especially on the weekend. It's hopefully getting better. So
Okay. So it is May 28th, 2025 as we record this. I'm in Phoenix and we are definitely burning. So we are definitely in our coming into our summer mode here. So yeah, we're up in the 38 Cs, somewhere around there right now. So very cool. Ghostbusters hat. Why do we have a Ghostbusters hat on?
I we did some presentations at the Swiss Comic Con a while ago, and they were, I think, doing promotion for that one of the recent new installments of the Ghostbusters movies, and I loved them as a kid, and I also loved the reruns, and it glows in the dark. So and it was and it was for free. That was
Oh,
the three
I won't
things. I
ask
always
you to
love
test
these
the glow
things.
in the dark here while we do this, but that could be interesting.
Yeah, and maybe so scientifically, I try to bust ghosts once in a while, or
There you go.
question assumptions, or maybe that you could interpret it this way.
Very cool. Very cool. Awesome background too, I gotta say. I love the little motion there on the planets.
NASA Visualization Studio.
Yeah, yeah, very cool. And Daniel, what do you like to do for research?
So my background is exoplanets. So I started with exoplanet transit observations in my early career. Even flew on Sophia a couple of times to look for these transits or to observe these transits. So my main background is spectrophotometry, to be a bit more precise, to really characterize these transiting planets, not just finding them. And then over time, I evolved more and more into this field of astrobiology, and more recently, I'm really deeply involved in the live space mission. So that's
Cool.
my job for the last 5 years, to be the project office lead for the live mission. Yeah.
Nice. Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. What if we find nothing? Bayesian analysis of the statistical information of null results in future exoplanet habitability and biosignature surveys. And Daniel, take us away.
Yes, so that's essentially the question we started with, right? What if we build these future telescopes and we find nothing?
Hmm.
Did we fail? Did we have a badly designed experiment? So what can we learn from not finding what we were looking for, what we built this? And this is what I discussed with, Amedeo and Angelica, Emily, Sasha, other people in our team. Also in the whole context of designing that future life mission, to figure out, let's assume the worst, if you want, case possible. We scan our galactic neighborhood for signs of biosignatures, signs of habitability, and we find nothing. What can we say? Can we say anything? And if so, what can we say? That's where
Good.
we started from. Yeah.
Good. Okay.
And then as an observer, with my observational background, I really, started thinking like, okay, let's fast forward to the future. We did the survey, the results come in, and now I'm sitting here as writing the paper in 20 years. How do I interpret, 50 non-detections of life? And then and then that seems to be like first order. That looks like a pretty easy statistical problems, right? You
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 would
you
think
you
so.
you you flip
Yeah.
a coin, 50 times, and then you know how rigged it is or not, or if 50% of the coins or the planets have life or not, or if it's 20%. So first order, it should be a straightforward statistical problem. But then if dig a bit deeper, as often in science, if you pay attention to more details, if you realistically model your observations and also the interpretation of your observations, then it gets more and more complicated. And this is what we wanted to tackle. So yeah.
Great. Perfect. Lovely. I'm with you. Hmm.
Yeah. So then then, as I said, I started to think, how would I interpret it? And then, since my background is, or I did a lot of work in Bayesian statistics in the past, and it's kind of like, the way many people are doing it. There's also, this frequentist approach to
Yes.
statistics, and I don't really want to, take a side, or make this big war between the schools bigger than it is. So
Yeah,
so
yeah,
there's
yeah.
essentially these two mathematical schools, which maybe we as practical mathematicians in physics sometimes use not in the right way, or we mix up
Mix up the
phrases, or
two.
what or intuitively, it's very similar, right? It's a belief for a Bayesian, and it's a confidence for a frequentist, maybe. But I think in the intuition, it's like, I'm confident, I believe, so there's a bit of, this lingo that is a bit different, but in terms of, interpreting results, interpreting our confidence, or the significance of a result,
Right.
could also show that they essentially
Give the same.
essentially the same.
Yeah.
If you observe enough planets, it doesn't really matter if you're a frequentist, or what kind of Bayesian you are. And this is actually one of the first answers we already found. So maybe if we go to figure one, then. So
Sure.
these are so. I hope that, at least a few of the people in the audience are familiar with Bayesian statistics. So
Oh, there we are.
you start with a prior. So the
Huh?
prior is essentially what how you define your belief before you even start doing the observation. So in our case, it could be the super optimist. You can say, oh yeah, life, is everywhere. 30% of the planets have life. So this is what we call the biased optimist here. So
Okay.
on the lower axis, you see this eta ops, which would be,
Yep.
the frequency of
Frequency.
planets that have this, or the fraction of planets that have this observable. So you can replace observable with life or with habitability. So this is, this would be the number 1.0 would be every planet has life, and 0.0 would be no planet has life.
Good. Yep.
In the K, and this is a distribution, so it's a density distribution. So in the blue case, this biased optimist would say, yeah, so on average 30% is my best guess, but it could be everything. And then the other priors we model there are what are sometimes referred to uninformative or low informative prior. And that's, again, mathematically speaking, there's no such thing. There's always a bit of information encoded in these priors. But
Yeah.
in that case, so this base Laplace or flat prior is what people
Yep.
usually use. And, in many cases already
Agreed.
make a relatively low information prior. But there's
Uh-huh.
also Jeffrey's prior, Carmen prior, and these extremely pessimist prior. And so we plotted them in linear space on the one side, and then in log space you can really see why it might be interesting to test these different priors, especially in the
Yes.
context of astrobology. So if you look at these flat prior, which is also flat in
Space.
log space,
Yep.
you see it still puts a lot of power on values between 10% and 100%. So in
Right.
that sense, it's and at least in astrobological context, if you assume that, it's still more than 10%, that's still pretty
That's
optimistic,
still pretty
or at
good.
least, it's not very very uninformed. Whereas the other priors, for example, this Jeffreys and Laplace prior, you see
Uh-huh.
they are kind of like bimodal. So it's kind of like this approach. So either it's everywhere or it's nowhere. So that's how you could interpret it. And I think this is, at
Yes.
least, and for some people intuitively, I think Dave Kipping said an interesting paper about it. It's a bit like if you want to solve salt in water. It either solves in every glass or in none of the glasses. It
There you
would be
go.
really a fine-tuning problem if life just appears on 50% of the planet. So this is why maybe these extreme priors are also a good way to approach astrological questions where you
Yes.
don't
Yes.
really know what's happening, right? So just to start with the lowest interpretation. So maybe if we briefly go to the appendix, to second appendix paper, there I did use the same priors to interpret.
Let's slide down to Appendix
Yeah,
A. Appendix A.
yeah, I think it's A or B.
Okay,
It's
so
a
on this one we
time
got
ago.
box
So it's
comparisons, and
this.
B we have, oh,
No,
here's the
it's B.
priors.
Yeah, yeah.
Yeah,
So
yeah,
okay. So this
yeah,
is
yeah.
this is if you would take these priors that I showed before,
Yes.
and then use them to compute the posteriors after 100 observation where you find one positive one. So
Okay.
this would be the how these different optimists and unbiased priors would interpret one positive observation in 100 observations. So
Okay.
we would do a survey of 100 planets, would find life in one, and you see all of them in. If you go linear space, they all have a very low number of the frequency. But then if you look at the log space, you see there's quite some difference. So
Yeah.
this Bayes Laplace or the Bayes optimist, they say, okay, we found 1 in 100, so the fraction is 1%, and we're pretty sure it's around 1%. Whereas the super extreme pessimist still thinks, well, we found 1 in 100, it could still be 1 in a million, right? So
Yeah,
this
there
is
you
how
go.
you
Right.
this is how you interpret these posteriors, and this shows that even if it looks in linear space, that if they agree, depending on what approach you take, if you're more optimistic, you still put a lot of power into these low
Low.
frequencies or
Yes.
these low probabilities that you have live. So that's an example why we use these different priors.
Cool.
Another reason to use Bayesian statistics and not frequentist is also because we kind of know that this number is at least larger than larger than zero, because we exist.
Yes.
So this eta life equals zero is wouldn't be there. And in
Yes.
frequentist,
Hmm.
if you do like a frequentist approach and you just flip coins and you just get heads, you would eventually say it's heads. But in our case, we kind of know, even if we find 100 heads, there's at least one tail that's us. So
Right.
that's why this Bayesian statistic is also slightly better suited to encode this belief that it's not zero without really biasing our result, if that makes sense.
Yes, I'm with
So,
you.
so, so,
Hmm.
so
Yeah, yeah.
that's one of the reasons why we use this Bayesian approach. So now we can come back. So now hopefully everyone gets the idea. So we model different priors. In that sense, we just imagine 5 colleagues. One of them is super optimistic about life, and the other one is super negative and says this rare earth theory or whatever. So this is essentially what we encoded with these
Rare.
different priors. And then we ask, if we give this result to these 5 different colleagues, how would they interpret with their priors our result?
There you
Okay.
go. Okay.
And then we go up. So this is, I think, then
Two.
figure 2 or maybe figure
Uh,
3. I'm not sure.
let's see. Let's go. Let's go.
Okay, let's figure 1. Yeah,
Here.
that's a bit of math. Maybe we can go a little bit deeper into the math later. So this is
Yeah, yeah.
um,
Let's do it.
um,
Do a little. Let's do.
so we are using this beta or this gamma distribution, beta distribution.
Uh-huh.
Um, then where do we have this? For example,
Wait,
if you go down, I think it's equation. This equation, for example. So this is a
yeah.
general definition. So you
Beta.
can yeah.
Mm-hmm. Hmm.
This
Yep.
is a mathematical distribution, and if you go down, or if you so this alpha and beta if you do this coin flip experiments, alpha would then be all your positive observations and beta all your negative observations in that sense. So in this, I think it's encoded somewhere,
Okay.
and it has some theoretically it's really easy to calculate. You don't have to
Oh
run
yeah.
an MCMC,
Well.
which other people run in and then you can design these priors also out of it. So for example,
Uh-huh.
if you set alpha and beta 2.5, you get this Jeffrey priors.
Yep.
The flat prior is if you set alpha and beta to 1,
Nice.
and then this solar system biased, you would add 2. So this would be someone who interprets our solar system already, or takes our solar system already in account, which obviously is a bit of a selection bias, or like we
E?
wouldn't be here if it wasn't for life. But
Yep. Yes.
in that approach, the optimist would assume, okay, we observed 3 planets in our solar system, like 3 habitable planets,
Good.
Venus, Earth, Mars, and 2 of them are not habitable and 1 is habitable. So that's
Okay.
what we encode with this alpha equals 2 and beta equals 3. So
I'm
this
with
is
you.
kind of like starting with a biased sample of our solar system in that sense. So
Mm-hmm.
this is a bit how this beta distribution works. So this alpha encodes your observation, or alpha and beta, encode, how many positive, negative observations you have. And then
Yeah.
it's relatively straightforward too. You don't have to, MCMC around it or do
Ah,
any crazy. So you can
right.
directly calculate. So you just update your alpha and beta to go from posterior or from one prior to posterior, and then you add the next observation. So it's really this
Good.
updating your belief with new observations,
Right.
which
New
you
info.
can see in the making actually. So this is why
Cool.
this is also for people who are new to Bayesian statistics, or this process of updating, modeling your belief and updating your belief with new observation, that's also maybe a nice way to get into this whole idea of, I do one more observation, I add one beta, or I do one more observation, I add one alpha, and this is how my posterior updates, so
Changes.
to speak.
Uh-huh.
Yeah.
Uh-huh. I'm with you.
Anyway, a lot of mathematics. If you don't get it, it doesn't really, it shouldn't really,
Change anything?
even if you didn't get all the details, it should still give you the idea how it works. So maybe if we scroll down, we can come back how to update this mathematically later. So if we scroll down to the second figure, then I think,
Sure.
um,
And here we go.
exactly. So this is the
Figure
figure two, exactly. So yes. So this is if we use these, color-coded priors from before, so the different optimists, Laplace,
Mm-hmm.
and so forth, and then we do, as you see on the lower axis, the number of observations in our survey. So we do 20 observations, 40 observations, 60 observations, and we assume we find nothing, right? So remember,
Okay.
our question is, what if we find nothing?
Okay.
And then here on the left side, you see what that interpretation would give as the best fit for this number. So let's say
Okay.
we observe 60 planets, we don't
Sure.
find life, and the best fit or best guess from this framework would be either, what is it, 8% for the biased optimist, and then
Yeah.
super low, or maybe for this Jeffrey it's about what is it? So you can see the best fit.
Yes.
But this is interesting already, but maybe not the most useful number. So we also calculated the 99.9% upper limit,
Upper limit.
which kind of means, so this is again, and in this we also compare to the frequentist approach. So it's
Ah, yes.
the frequentist is a confidence interval, and
Mm-hmm.
in the Bayesian statistic is a belief. So it's mathematically not the same thing, but I think
Right.
intuitively this is our 99.9% upper limit
Mm-hmm.
that would be derived. So in other words, if we do this survey,
And you get
we
60.
would we would only be 1 in 1,000 time our result would actually be outside of what we derive. This is how to read this
Got it.
99.9%. So this means we are pretty sure that whatever the real number is probably below that number, right?
Yes.
And then you can see here, so we compared these different approaches, and then you can see, for example, if we do 40 observations,
Okay.
and we don't find any life, we can very confidently say that the frequency of planets that have detectable life is smaller than 20%.
Yes. I'm with you.
And it doesn't, and then you can also see, the more observations we get, the smaller the difference between these different prior scores,
Go.
right? So if you
Right.
do 100 observations and you don't find life, the optimist and the pessimist, they get, as it should be, right? They should get more and more. They should get more and more on the same page, right? And you can also
Correct.
see the frequentist and the Bayesian approach. They are also converging. So that means either
Mm-hmm.
if you're a frequentist or more into Bayesian statistics, you would still interpret this upper limit on pretty much the same levels. So
Yes. Once you get high enough and
that's
in, they're the same. Mm-hmm.
okay. So that's the first take-home message here. So we observe, so these future telescopes. We also come to this later. If you build this, and this is in general for any survey, even if you would, I don't know, search for all the elephants in the savannah that are pink or something like this. You would all
Right.
you could use this, and then after 60 elephants that you check, this is not just for exoplanets. So this is a very general statistical framework. But
Mm-hmm.
here we know, so if we build a survey like this, we should aim to get 40, 60, maybe 80
Okay.
Earth-like planets, or whatever population you want to study, right? So
Got it.
this is kind of the first sanity check. So these future surveys aiming for that number of planets, even in the case we don't find anything, we can at least get a pretty robust
We'll say
and
something.
relatively low upper limit or lower limit of the frequency of habitable planets. So
Uh-huh.
that's the first thing we looked at. And here comes the catch, and here it's where it gets a little bit more complicated than
Yeah.
just this, pure Bayesian statistic. This assumes that every observation is perfect, right?
Right.
So that we observe a planet, we put our spectrometer at an Earth in 10 parsec, And after, 10 days of observation, we can say I'm 100% sure there's life, or I'm 100% sure there's no life, right?
Yeah. Yes.
And, this is, of course, not happening, right? First of all,
It's
we're
not
never
realistic.
100, we're not 100% sure of anything in science anyway.
Right.
And people who are a bit in this field, they know this. It's a big conversation in our community. What is this? What are the confidence scales? How do I parameterize? People say, okay, I find oxygen and methane. That's a biosignature, but what is it? 80%? Is it 95%? So how do you how significant is that how sure can I be? People suggested other Bayesian frameworks to derive some number. How do I put a number on my confidence that I found life in this planet or not?
Right. So we
So
have to
this is
follow on
this
uncertainty.
is
Hmm.
exactly. And this is what we see here is like for perfect observations, right? Assuming
Yes.
this laboratory case, it's a clear coin flip. Every planet we look at, we get a clear answer. But we have the standards of evidence, scales, and whatnot. So there's a huge discussion. There's also discussion about we may not ever know, because there's could always be some abiotic sources for
Yes.
certain biosignatures that we haven't even conceived yet. So this is
Yes.
almost a philosophical question or epistemological question, right? There could always be explanation that we hadn't thought about. So
Right.
it very quickly also becomes very philosophical. What does it even mean to be confident in the individual observation? But we broke that down in two different mistakes, so to speak, that we can make in our observation.
Okay.
So one would be what we call, a sample uncertainty or sample bias. So essentially, the planet we look at is not from the population we want to look at.
Okay.
So let's say we want to get the fraction of rocky planets in the habitable zone that have life, and then
Oh,
somehow a super Earth sneak in, or somehow a planet that is slightly outside the habitable zone
yes.
sneaked into our sample. So what influence would that have on our result?
Right.
And the other is what we call interpretation uncertainty or interpretation error. So if we do an observation, let's say I look at a planet, I get that mid-infrared spectrum with life, I find no traces of oxygen and methane.
Okay.
Am, am I 80% sure I can exclude life? Am I 95% sure I find life? So we put different levels. So we don't we leave it to people to come up how they get to this number. So we're not giving any recipes how to derive, I'm 80% sure, but assuming someone tells us I'm 80% sure I didn't find life, I'm
Okay.
95%
Okay.
sure I didn't find life, what would we get out of this?
Fair
And
enough.
this is when you scroll down to
Figure three.
figure three. So this is the same plot as before. In this case, we only used one of the priors, so this Jeffrey's prior, because that was
Fine.
kind of like the average one.
Okay.
And then you can see on the again on the lower axis the number of planets. The more
Yeah.
you observe,
There
and
you
then you
are.
see on the top the sample uncertainty. So for different sample uncertainty, so 50% would be
Good.
even half of the planets in our sample
Okay.
are even not from the group we were looking at. So that is a
Uh-huh.
pretty
Uh-huh.
extreme case. But then we just need to observe more, right? So if we really don't find anything, so you can imagine, if we observe 50 planets where we are super sure that they are from the sample, we should get the same result as if we observe 100.
Yeah.
So this is still something we
Right.
can cover, right? So if
Right.
you know 10% of my planets are not from my sample, then just observe 10% more, right? So that's not that big of a deal. You can see still, it still goes down. You just have to observe slightly more if you're 50% unsure. So that's maybe, I mean, it's still,
It's
good to have a
comparable.
it's
Right.
still good to have a clean sample, but it's not completely killing us if we
Yes.
if we have 10% of super Earth in our, at least for that way we phrase the question. The
Okay.
more interesting one is the lower one. So this is when we
Yeah.
get this interpretation uncertainty. So if I'm only if I always have this 20% uncertainty that okay, I can't find life there,
Yeah.
but there's still a 20% chance that there is something we
Something,
haven't
huh?
seen, something, that I can't interpret. Then that essentially defines your upper limit in a sense. So if you're only 20% sure in each of these cases, you can never push your upper limit below 20% in that sense, right? So this is in short what they said. And then you can see, you know, the more uncertain you are about your individual yes or no, I observed life or not, that really then pushes that upper limit much higher, right? If I'm only 20% sure, you see, even if I observe 100, you know, my upper limit is somewhat at 40% or something.
Thereabouts,
like
yep.
So this means, you know, and this is where then, you know, we have a bit of a call to action, if you want, to the community. So I think this is really something we need to get our act together, so to speak. And this is what I was mentioning before already. We have these, you know, these standards of evidence, you know, we trying to develop these, you know, Bayesian frameworks to actually put numbers on it, or also to, you know, to find a metric for our uncertainty. So this is stuff that people are working on, but this shows actually in action where it might be really needed.
Okay.
And the other thing, it really also gives a bit of a guidance how to ask the right question.
Oh, that's
So
fair.
if I find if my question is, you know, what is the fraction of planets that have life, this uncertainty is going to be really high, because first of all, we can only detect life if it makes an impact on the whole atmosphere, right? If it's a single microbe under a rock on an exoplanet, we will never remotely detect it. So the first thing is, you know, we probably have to at least adjust the question to, you know, which fraction of planets have a detectable or have a biosphere that is big enough to change the atmosphere on it. You know, you see it gets, you know, the questions get more and more concatenated if you want to, you know, push it down. So what we recommend is not necessarily to look for the fraction of planets that have life, but maybe look for the fraction of planets that have a certain threshold of oxygen, or that is in a certain temperature regime, or that shows phase variations, or something that is actually directly connected to a measure, because there's always this step of interpretation, right? So if you have oxygen and methane, then you interpret, okay, there's life, but what is the uncertainty on this interpretation, right? This is, you know, I mean, again, a very philosophical, very, you know, philosophy of science question. So if you rather than phrase the question of which fraction of my planets are Venus-like, that's still a bit vague, right? But if I say which fraction of my planet have more than 2 bars of CO2 and are hotter than 350 or something like this, then that's something that is much precise, and they can put much lower error bars on than this vague, is it Venus-like or not, right? So this is a bit of, you know, first, you know, guidance how to, you know, find a remedy for this problem that we don't have these perfect observations.
Excellent.
Yeah, so that's that about this. And then I think in the last important plot, we also compared this to future telescopes. So namely the Habitable World Observatory. So this optical, so this UV to near infrared concept to observe habitable planets with a coronagraph in the reflected light.
Yes.
And then on the other side, the live concept that we are planning, designing, and working on here on the European side, which is using a technique called nulling interferometry, which is a whole other can of worms that we might not take this time.
We don't have this time to do it, but
yeah. But it's similar to coronagraphy. It really is direct imaging of the planet. So you suppress the central star and get a spectrum of the planet itself.
Yep.
And that's then done in the mid-infrared. So we will get with this live, we would get the actual emission of the planet, which has some advantages and then some disadvantages in comparison to HWO. So the main story here is ideally we get both of them. Both together would, you know, as always, you know, it's more than the sum of the individuals. So having both will give us a really, really good shot to scan our neighborhood for forms of life. But here we compared to what people projected would be the yields of these missions. So there's this paper by Morgan and al. From 2022 where they calculated for how many planets they could do a search for water and for how many planets they could do a search for oxygen.
Okay.
So in that case, and these numbers is, depending on some assumptions, it's this blue line is like the best number they get out, and then this shaded area is like the minimum or maximum. So I think
Right.
in that case they had, I don't know, I think they might have 18. The numbers should be somewhere in the text, but it's, let's say between 15 to 27 where they can search for oxygen, and
Yeah.
between I think 18 and 38 where they can look for water. And then you can see, if we do this, if
Okay.
we would do this survey with HWO, we would look for these, 18 planets, search for water, wouldn't find any water. We could already say that the fraction of planets with water is lower than 25% and something. And then the same exercise on the other side
Right.
with
Right.
two different installation or two different designs of the LIFE mission, one with 2 meter telescopes, one with 3.5 meter telescopes, also shows that we cover this space where we would eventually get also interesting numbers,
That's
or can
fire enough.
really push the upper limits.
Oh,
Uh,
shit.
there's also there's also, if you scroll down, there's also another one to make the live mission even look a bit better in the because it's a bit comparing apples to oranges in this plot. But if you scroll down to the appendix, so this is. So this is if we go to the optimized habitable zone and FG and
Okay.
K star. So no, I think it was the plot before. It's slightly, you can see this. It's slightly bigger number for the live telescope. So with the live telescope, we would probably get around 40 of them, right? Still a big error bar depending on how really frequent they
Okay.
are. And so between,
Okay.
15 and 80. So, and this is also where we show, if we get
Yeah.
live, we get roughly 30 of these Earth-like planets in
Okay.
the optimized habitable zone, or the optimistic habitable zone around FGK stars. If we don't find anything with the live mission, we would at least have, upper limit of 15% for
Yes.
the fraction of planets who have this feature we are looking for.
Yes.
So that's
Right here. Yep.
that's the message here. So again, a
Cool.
bit of a sanity test, if we aim for survey sizes of 50, 40, 50, 60, we will be first of all independent of our prior assumptions. So either if
Yes.
you're optimist or pessimist, you get enough to converge,
Yes.
and it's also enough to build a number to get a statistically significant upper limit, which then might be helpful for the rest of the astrology community to
Yes.
derive other theories and so on. Yeah,
Cool.
so I think that's in a nutshell, or little bit bigger in a coconut shell, what we
Coconut shell.
what,
A
what we did
Ghostbuster shell. How about that?
here, right? So
Very,
not a small nutshell, but this is essentially what we did in the paper in the
very
main
cool.
findings. Yeah.
Very nice. Beautiful work. Beautiful work. Daniel, I want to thank you so much for walking us through your very awesome AJ article.
Mhm. Thank you.
Yeah,
Was a pleasure.
sure. And you kind of touched on it a little bit as we went on through. And so let me go ahead and push on that a little bit and ask, where do you think we go from here, given the published article? Are there maybe additional priors to do? Is there other frameworks one might want to consider? Maybe there's some other telescopes, let's say, that were coming online soon that may be able to help inform some of this. And so where do you think we go from here, given this published article?
So personally, I'm already working on generalizing this framework.
Okay.
So the working title is "How many exoplanets are enough?" So
Yes. Yes.
it's a little bit turning around the question. If we assume a certain frequency, how many do we need to observe to at least find one, for example? So you can ask this, and then you can use the same. But if we are only 80% sure, we probably have to look at a couple more to be really sure to find one. So a bit turning around this question, or generalizing this question, not just what if we find nothing, but what do we have to do to find something, so
Something.
to speak. So to make this a bit more generalized. Yeah, and then I hope that I mean, there's also other statistical frameworks, looking from slightly different angles at it. So there's also a lot of work done there, more concrete work. Can you prove the habitable zone concept? Is a paper that we just pushed actually just 2 days ago, which is interesting. So
Okay.
not
Okay.
just get a fraction, but to really, can you statistically prove any trends that you predict? Yeah, and then I really hope it's one additional argument for people to really start thinking more about this step from detecting molecules to really say it's life or not. So because this life, yes, no question, we need to put a number on this. This
Got
is, we can't do statistics this vague. I think, I guess, I believe it's life, right? So I think
it.
this the standards of evidence. I mean, we had the discussions over the last couple of weeks. What is a detection, and is that detection a biosignature, and is that really, and so on, right? So there's a lot of things that point us that we as a community should work on these kind of things at the moment. Yeah.
Very cool. And remind me, what is the anticipated launch date of the Life mission?
It's in, I mean, optimistically,
Yeah.
I mean, if we won the lottery next week and we can maybe build it in 10 years.
Okay.
But I think realistically, I mean, or like realistically 2040, and then in the early 2040s, I guess it's also there. So ideally it would fly at the same time as
Ooh,
HWO.
that would
So
be very cool. That would be
which is
great.
also, I think, early 2040s, right?
Hmm. Okay. Good. Well, it'd be really
But if
exciting.
anyone out there, wants to build a space telescope, talk to us. We can build it in 10 years. So,
There you go. There you go.
yeah,
So that's a great Kickstarter campaign slogan
yeah,
right there. So yeah.
yeah, right. Yeah, yeah,
Very
yeah.
cool. Well, it'll be really exciting to see this develop over the next couple of years, particularly as we firm up the questions and what we can answer and what we can't answer
Mm,
with some degree of certainty. So it'll be really nice to see this develop over the coming years.
mm,
Very cool.
mm.
Very nice. Daniel, I want to thank you so much
Yes.
once again for walking us through your.
Thanks for the invitation. Yeah.
Yeah, sure. And that will do, everyone. And I hope this made your astronomy day, your exoplanet day, just a little bit better. And we will see you on the next one. Bye bye.